All right, it's 11:15, so we'll get started. So remember, we are in exam preparation week. I'm excited too. Yeah, I sent you some material last night. I posted a practice exam as well. The Canvas dates on the exams might have been off because Canvas has a really hard time figuring out what year it is. And so I've tried to correct those. But remember, the syllabus, the PDF syllabus is the rule that we're going to follow. Canvas is a course aid. It helps us communicate, but the rules and regulations of the class are in the PDF syllabus on OneDrive. So if you have a question, or if we get off track, we're going to look at that PDF syllabus. We're not going to look at the weird stuff that Canvas does. You should be thinking about your exam, when you're going to take it, where you're going to take it, how you're going to do your written part. You need some blank pieces of paper. You can have some scratch paper. I give you an equation sheet. That's the only sheet that you're allowed to have other than blank pieces of paper. You should have a pen or a pencil. You should be approaching the written part just like you approach the homework, nice and neat, all that stuff. And so we only have two big things to cover before that exam. We're going to cover them today and Friday. We're going to review on Monday, and then we should all be set. There's extra office hours available. There's still office hours this week. I'm available by appointment, but you should be, starting to feel it at this point. Questions? Yeah. So the Canvas part is 70 minutes time. So I think it's going to be 20 questions, 19, 21, something like that. That's time. Canvas will lock you out after that. The written part is honor system. You can download the written part or bring it up on your screen and just write the answers on a blank piece of paper. Written part, question 1, written part, question 2. You take a picture of that, submit it on the Canvas Dropbox, just like you submit homework. And I'm expecting that you submit that 30 or 40 minutes after you finish the multiple choice part. The exam has to be taken all at once. I can see exactly when you stopped the multiple choice part, and then I can see exactly when you submitted the written part. So I'm expecting a good, reasonable time between those two. If the written part won't be super long, it won't be like the homework. It'll be like 3 questions, and you'll be able to look at them, write it down. You won't need lots of calculation or anything like that. You should have a calculator because we're going to talk about some calculations today. But I think to give yourself enough time on the exam, you should sort of have an hour and a half to do everything, and you should be A-okay. Yes?
So you said for the written part, you prefer to not be on a tablet or paper?
Yes, paper, picture, yeah. Because I think that's the best way to learn some of this stuff, including when you're studying. We're going to talk a lot about the functional groups today. You want to be writing those down, and it's just easier to put it in your brain if you do it on paper, I think. Yeah. Yes. Yes, I think the exam, I'm going to open it at 8 a.m. unless someone wants to get up at 6 a.m. and do it. I'll make an exception. But it closes at 11. It's not going to close at midnight. Nothing good happens after 11 p.m. And you still have your written part to do. And so it will be open all day, but pay attention. Don't start it at 10:30 p.m. That's not good exam strategy, right? Because I think Canvas does stop you right at 11, so you won't get the full time. But it'll be open a good span of the day. Don't forget about reloading. That is, we haven't had many Canvas exam problems the last 2 years in this class, so I know sort of how the exam works. The one problem we have is this reloading issue. Reload, 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 use Firefox, and it should come up. Yes?
So is the open-ended part also do 11?
You want to do a reasonable time. So if you do finish the exam at like 10:30 and you turn it in at 11:10, that's fine. I don't think the Dropbox will be locked, but I mean, you just don't want to save the exam until, that late. Yeah, just give yourself some time. Other questions? All right, so the practice exam is posted, the equation sheet's posted, all the notes are posted, homework 2 is posted. I'm going to post the homework 2 solutions, homework 1 solutions are posted. So you're starting to get a lot of database information for helping you study for the exam. All right, so this chart is really interesting because it shows the different types of key polymers. All of these polymers, except for polyurethanes, have a recycling code. And it shows you the percent of what's made. So you see that the big ones are polyethylene and polypropylene, right? That makes up a large part of the polymers that are produced. And what type of monomers do we use to make polyethylene and polypropylene? What's that? Yeah, so we use vinyl type or carbon-carbon double bond type monomers, right? So that's why we learn about those types of polymers. That's why it's important. Even if we include PVC, we get down there, right? Now we have polyurethanes and polyethylene terephthalate. They're a smaller percentage of the overall polymers, but they're used in some really important applications. Polyurethane foam, for instance, or PET packaging, right? All those clear drink bottles are almost exclusively PET, except the new Nalgene bottles that are a different type of polyester, not polyethylene terephthalate. So that's interesting. So if you want to have an impact on the polymer pollution problem, the big ones are polyolefins, right? Ethylene, propylene, etc. And here are the polymer use broken down, or the polymers broken down by use. In packaging is a huge one. There's a lot of cheap polymers like polyethylene and polypropylene that's used in packaging. And so if you care about microplastics and care about plastic pollution, that's the big fish to fry. Also, what I didn't know until last year was that a lot of microplastics that we find in aquatic land-based bodies of water, like rivers, streams, the Chesapeake Bay, stuff like that, the Susquehanna, are dust from car tires. And so it's not necessarily people, taking their water bottle and throwing it in the Susquehanna. It's cars driving around and those tires are wearing away, and they create a lot of microplastic pollution, which is really interesting. And so figuring out what to do about microplastics from car tires is a real problem. And of course, recycling car tires is hard anyway. But that gives you some idea of the landscape of use of polymers, the type of polymers we're talking about in class, and then this issue of plastic pollution, which I'm hoping a few of you out there have a really good idea how to work on this problem, because we need it. Was there a hand up in the back? Yeah. Oh, sure, go ahead. That's right, because the writing is similar to the homework. So you can practice the written part of the exam by getting the homework questions and doing that. Yeah, that's right. And similar to the clicker questions, things like that. So there is no written practice part of the exam because it's similar to what we're doing already. Yeah, I just wanted to give you enough multiple choice questions so you sort of get, how I ask multiple choice questions. You sort of get, what I'm going after, because the practice exam is really important for the topics and to practice multiple choice questions. You practice the written part of the homework. Is that cool? Yeah, and that's why it's really important to do, the homework by hand so you get used to drawing all those structures. All right, any other questions or comments? Okay. So we talked about this last time, and you can just get your clickers out, but we're not going to click this one. So we talked about our addition polymers, right? As soon as you see a monomer like this, you think addition, polymerization. And I'm going to abbreviate polymerization PCN. And so that's chain growth, addition polymerization. You know the features of that. we're going to leave that aside for now. That's all you need to know on the exam. PVC, ethylene, propylene, styrene, the main features of addition polymerization, how to turn this into a polymer. And we're going to turn our attention for the next couple lectures to step growth polymerization. And so if you're wondering what's going on with addition polymerization, if you're wondering what the monomers look like, if you really don't know what polyethylene is just yet, you know, that's something that you're going to have to study on your own, because we're not going to talk that much more about it other than in review. We're going to really focus on step growth because there's one or two big things left in step growth to talk about. So if you have addition polymerization questions, ask them in class, ask them during office hours. So we wound up here on step polycondensation or condensation polymerization, or however you want to call it. And we talked about the different monomers that we use to build up these polymers. Is that a question? No? Okay. And so you should know this because there are different ways to make very similar polymers and different monomers. And so on the homework, I gave you some polymer structures and said, please break those down into their constituent monomers. You should know how to do that. And if I give you a mixture of monomers and I say, please show me what a polyamide, what two monomers you would use to make a polyamide, you know which monomers to pick, and you can draw the polyamide structure. So you want to be able to go forwards and backwards with these types of problems. And so we wound up here last time. Now this is a little bit different of a structure than you're used to, right? Because phosgene is a really unique molecule. But if you look at it, it's a carbonyl right next to a chlorine. And so you know that's an acid chloride. And you know the acid chlorides react with alcohol. So even if you haven't seen phosgene before, you should have a reasonable idea that, okay, you know, I've got an alcohol, it's reacting with an acid chloride or a carboxylic acid if you know you turn that acid chloride into a carboxylic acid. And the new functional group is a carbonate linkage or a polycarbonate linkage. And so you want to commit this to memory in terms of what the functional group is, what a carbonate is. So it's an oxygen on each side of the carbonyl, and a couple of examples of monomers that go into a polycarbonate. Because on the exam or on the written part or in the multiple choice, I could say, write down the chemical structure of a polycarbonate polymer and write down the chemical structure of the monomers that you use to make it. That is totally fair game on the exam. And you'll have to commit that to memory. I'm going to give you an equation sheet so you don't have to memorize the equations and the math and all that stuff. But I'm expecting you to engage with the molecules and know those. You've had the prereq, you know, organic chemistry is a prereq for this class. So I'm expecting a little bit of memorization when it comes to what the molecules are. Yes.
So what if you're just given the polymer, like the actual polymer formation? How would we actually know that phosgene would be the actual monomer for that?
Yeah, this is a special case. I mean, this is as hard as it gets, right? But you say, okay, you know, I've got this polymer. Well, let me just get a fresh one. I've got this polymer. And I know that's polycarbonate. And I remember that I at least have a diol to make a polycarbonate. So the most likely alcohol is going to look like this. And so I think you can get back to bisphenol A, and then you think about, well, what's left? I've just got this carbonyl sticking out there. That's not part of the diol. And how do I get carbonyls in my polymer with diols? I can say that this should be a dicarboxylic acid, but it turns out that we don't use this molecule. That doesn't really work. You say, okay, phosgene is special. And so I use an acid chloride. So it is a gray area whether you use a diacid or a diacid chloride, because they give you the same result in polyesters, polyamides, and polycarbonates. And so it will be open. I mean, that's why I will either be really clear on the multiple choice, or you get to pick whether you use a diacid or a diacid chloride when you break this apart. But you need to be savvy about, okay, this looks really familiar. This looks like a diamine. I'm going to pull that out. And then what's left? And what do I need to do to make that polyamide? Yes.
This may be straight on the question, but do you mind explaining how exactly the polymer there is actually applied in it? Because I'm just trying to like see how.
Yeah, no, that's not a dumb question. And so if you just glance at this thing, you say, I have an ether here and I have an ester here. But remember what we talked about in previous lectures, to really figure out what the functional groups are, you take that repeat unit, you can slide it over and connect it to the next repeat unit. Slide it over, connect it to the next one. And if we do that, we know that this oxygen is connected to this carbonyl right here. So you have O carbonyl O, and that is a carbonate linkage. We could easily put the parentheses here if we wanted to, put the parentheses here, and then put the O here, and put the parentheses there. That's fine. That's just sliding the parentheses up and down the molecule. But you need to be savvy about this, or you need to rewrite the polymer structure so you understand, okay, I can move those parentheses around and it doesn't change the repeat unit structure. I will likely ask you to do that on the exam. So you want to look at that example. Here's the repeat unit. Is this repeat unit the same or is it different? And so you need to be counting atoms, figuring out where the functional groups are, all of that stuff. So you should be flexible in terms of how these structures are represented. Yes.
So if we weren't given names, so like the bisphenol A and phosphine, when breaking down the polycarbonate, would you expect us to call it bisphenol A or diols?
That's just be able to write the chemical structures. You won't have to memorize this molecule's phosgene. You won't have to memorize this is bisphenol A, but you should be able to write the chemical structure. So I'm not going to quiz you too much on nomenclature other than this is a diamine, this is an amide. I'm not going to ask you nitty gritty details. I might ask you, about styrene, but you should know that. I'm not going to ask you sort of the really niche stuff. Yes.
I read the textbook that you can also use bromine. Is that true?
Oh, you can use the phosgene with 2 bromines on it?
Yeah.
Yes, because you know that halides are good leaving groups. And so in this case, the halide is the leaving group for this. And so you could use the dibromide there if you want to, or diiodide. Good. Okay, this is really important. And you're going to have to study this, make some flashcards. If this is not like right at the tip of your mind, just make some flashcards, study them. You've got plenty of time. All right. So what are the functional groups? What are the monomers? We're going to focus on this the next 2 lectures because you're going to have to know this on the exam. So addition polymers should be easy at this point. Step growth, we have some stuff to learn. All of these groups are fair game. So I'm going to star this slide, make flashcards, know what the monomers are, know how to break these apart, and we're going to focus on this. And so you want to know what an ether is. You want to know what this is also called a thioether for obvious reasons. Polyesters, polycarbonates, polyamides, polyurethanes. This is a tricky one. We're going to talk about that. And I think you have polyurethanes on your homework, and polyureas. And so you should be able to recognize these functional groups. Even if I put the parentheses in funny places, you should be able to pick out the functional groups and then break down these functional groups into the monomers that you need to put these functional groups together. But this is the key slide. If you know these, know how to make these functional groups, you'll be fine. Yes.
So are the squiggly lines just how like the actual chain of the
That's right. The squiggly lines are the polymer chain. So you don't actually know the monomers, right? The monomer for let's do polyamide is this squiggly line C O. Let's do the acid chloride plus squiggly line NH2 and H2 gives you a polyamide. So you don't know what the monomers exactly are because I just show you that it's a polymer chain. Usually you'll have to show me the real chemical structures. Usually I'll ask you for this, but don't be thrown off by squiggly line means polymer chain. We don't know what it is, or R groups if you want, or something like that. So again, memorize this slide, know it forwards and backwards, making polymers and breaking polymers up into their monomers. And so if you can figure this out, and if you have good flashcards and good analysis or good recognition of these functional groups, the chemistry questions won't take very long because there's not many choices, right? And so this is something that you really want to commit to memory and get comfortable with to build some expertise in polymers. Any questions? Okay, this is the one thing you'll have to memorize. You won't have to memorize any of the math that we're going to talk about in a second. All right, polyesters. This is an ester, and because it's got those squiggly lines, it's connected to a polymer, so that's polyester. And you know, in polycondensation or in step growth polymers, we have our Ra2, Rb2. We have different ways to do it, right? We've got our carboxylic acid, or we've got our acid chloride. Remember, you get exactly the same polymer with an acid chloride or a carboxylic acid. What's the difference? What's the real difference between using a carboxylic acid versus an acid chloride when I make these two polymers? Yeah. The extra small molecule, right? The condensation product. So if I give you this and say, tell me what those monomers are, you have to use the diacid because that's the only way you get water as a small molecule product. Or if I give you this, of course, you have to use the acid chloride because that's the only way you get HX, HCl, HBr out of there. So there are little clues. If I don't give you that information, it's up to you to pick whatever monomer you're comfortable with, whatever you get, whatever makes sense. You know, there's no right answer unless I give you that extra information. All right. And the one thing that we'll talk a little bit about is this ARB. So this is called an AB polymerization. And notice that it's both functional groups in the molecule. So the functionality here is 1, 2, and I know that I've got my acid, and I have an alcohol. I know that's going to be an ester. I memorized it on my flashcards. Boom, I have my polyester. But this structure looks different than these structures because I have R1, R2 in the top structures, and I only have one chemical structure between the functional units in that ARB. There's also another super secret to figuring out what's going with ARB polymers versus AABB polymerization. And that's this right here. You see R1 is between two carbonyls. So both of those carbonyls belong to R1. And so when you write the monomer, you have to write it like this. And here, R2 is between the oxygens. And so that's likely going to be the diol, right? And so the oxygens both belong to R2. And if you look really closely, there's ester, R2, ester, R1, ester, R2. R2 and R1 alternate, whereas in this, it's ester, R, ester, R, ester, R. Those chemical structures are different. And so you should be able to recognize how to break apart these AB polymerized monomers and how to recognize when you have an AB polymerization. That's a little tricky. Practice it. Think about some scenarios. Ask questions. Yes?
So I'm really confused what outside the actual brackets, why there's no H in the H in the first line, and there's X in the H.
Yeah, N groups again are funky. I mean, sometimes we'll draw extra monomers. You know, this is basically preserving the end of this monomer right here and preserving the end of this monomer right here. I mean, you have a question on end groups in the homework. If I ask you about end groups, you know, you want to write them in, but for the most part, we'll leave the end groups off. But this is basically, this end group residue here is this guy. It hasn't reacted with the diol, and this is the end group residue right here. It hasn't reacted with the acid chloride, so we just stick them on there. So even when we put the end groups on, remember, since we have this parentheses with the end, we can slide that structure along, right? So this is not, well, this is only an alcohol end group right at the end of the chain, but it is a polyester because this structure is repeated and that oxygen is connected to the carbonyl. So it's polyester, 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 polyester. Oh, the end group is alcohol and the end group is in acid chloride, but that's only one at the very end. Questions? Okay, this is new. It will take some studying, but you've got plenty of time. And here's our example for PET. It'd be really helpful if you just knew how to do this, how to draw this. If you memorize these monomers, otherwise you can memorize your own set of monomers for polyester. I'm not going to be super picky about what you put for those R groups as long as they make chemical sense. And so this is at least one to know. It's one of the most important polymers for plastic pollution because there's so much, there's so many bottled drinks out there. It's a real issue. All right. Next thing you want to memorize is polyamide. We've talked a lot about that. You should probably memorize that polyamides are also nylons. That will help you in the future because nylons are used in lots of different engineering applications. And so this gives you a little bit of leg up for people that don't know the chemical structure of various nylons. They're used in 3D printing. They're used in lots of automotive and aerospace application because they're relatively inexpensive and they have really good properties, better properties than polyethylene and polypropylene. This is a polyamide. Here is the Ra2, Rb2 in carboxylic acid or acid chloride form. Again, because we know that we can make an amide group if we take our diamine and we're going to focus on primary amines, so RNH2, and we're going to make our polyamide, same as we did before. Here's the AB form. We have our carboxylic acid. We have our primary amine, and you know you can turn that right into a polyamide. So I know that we're still learning this. This is one of the first times you've seen this, but you really want to look at these slides to make the chemistry questions not as hard as they sometimes are. You want to commit this to memory. So notice again that these polymers are different than these polymers. So who's heard of nylon 6,6? Yeah, nylon 6,6 is the nylon that we usually have in the United States and use a lot. Who's heard of nylon 6? What's the difference between nylon 6,6 and nylon 6? Yes.
Would it be that nylon 6 is made by Ra2 plus Rb2 and then nylon 6 would be made by ARB?
Perfect. Yeah, nylon 6 is made by ring opening, which we won't talk about right now, but it's kind of an ARB. But nylon 6, R equals 6 CH2 groups, and nylon 6,6, R1 equals 6, or actually R1 is 4. Whoops, sorry. 4 CH2 groups, and R2 equals 6 CH2 groups. Because when we name nylon 6,6, that carbon is counted and that carbon is counted. And you notice that nylon 6,6 has a different chemical structure than nylon 6 for the reasons that we've just talked about. And the reason that nylon 6 was invented is that the patent was already there for nylon 6,6, and people said, well, this is a really useful material, but I want to improve my commercial viability. I'm going to invent nylon 6 and get around the patent for nylon 6,6. Very interesting. And so again, you just need to be aware of what functional groups it's going to take to make a polyamide, or if you see an acid chloride and an amine, you know that's going to be a polyamide. So you're able to go forwards and backwards in these chemical structures. Any questions on? Yes.
So nylon 6,6 and nylon 6 are definitely different in structure. So would they have slightly different properties, or would they be somewhat comparable?
They have slightly different properties. The hydrogen bonding of those amides is a little bit different depending on exactly the chemical structure. So nylon 6 and 6,6 do have slightly different properties. Yes.
So we're just giving like a polymer for every polyamide, like the first one and second one. How do we know exactly which is going to be a carboxylic acid or an acetylide?
Yeah, so the way you know is that you have to have extra information about the small molecule byproduct. If you don't have that information, if I don't give that to you and just say, give me the monomers for this, you can use either one. Maybe on multiple choice, there will only be one available. So unless you have extra information on the small molecule byproduct, you won't know, because these are exactly the same polymers. Good questions. Any other questions? All right. Let's see. So this is an amino acid. And so amino acids, they call it an amino acid. This is the same stuff, that we use. It has the amine group and it has a carboxylic acid. That's the origin of the amino acid name. And so when we take an amine and we would react it with the carboxylic acid, what do we get? Polyamide, right? This is ARB polymerization. And so this is a representation of a polyamide, and that's what all proteins are. So as we put together these building blocks of life, they're basically polyamides. Kind of like nylon, although they have special properties. Of course, they fold up in really interesting ways. How many amino acids are there? Natural amino acids. Yes. I think it's 21, 22, something like that. So imagine all proteins that life is made out of only have 22 monomers, or 21 monomers. That's really interesting. Of course, DNA is different type of monomer, but there's only 4 monomers in DNA. So nature does really awesome things with just a couple monomers. So that's an aside, but you should definitely know that this is a polyamide. Whether you know it's a protein or not, that's not going to matter too much, but that's just an interesting polymer factoid for you. Other questions? Okay, we're going to keep going, then we're going to take a breather, because I know this is a lot, but I want to get this information out to you all so you're ready for what we're going to do next week. Polyethers, this is an ether. It's not connected to any carbonyls. It's not connected to any nitrogens. What are oxygens connected to in ethers? Carbon chains, right? Carbons with nothing on them, or aromatic groups or something like that. And so you really don't want to call this, you really don't want to call this an ether, because it is next to a carbonyl group. So that's an ester. Polyethers will either be nothing that you recognize, or they'll be all connected to carbons. And the way we make polyethers is we do it through this special type of polymerization called RA2. And so here we have a diol, and in the presence of strong base, we can make a polyether. So it's a repeating R oxygen, R oxygen, R oxygen structure. That's the polyether. And we still get a small molecule because it's condensation polymerization. Now you will have to know, or there will have to be some hint in the problem, like I'm looking for a polyether versus if I put some acid chloride in here, right? It's probably going to be a polyester. So I won't hang you out to dry in terms of, am I looking for a polyester? Am I looking for a polyether? There will be clues about what type of polymer I'm looking for, but you have to be savvy about it and read the question carefully. Yes?
Are they exclusively RE2 reactions or PE reactions?
Can you react what? I mean, this is the only way to make a polyether or to get the structure we want, right? Because I mean, what other monomer would you propose? Yeah. So I mean, there's really no way to make an AB monomer because you still have an OH group at each end of the monomer, right? And you're basically saying that alcohols react with alcohols to give ethers. Yeah. I mean, there might be some strange exceptions, some ring opening polymerization, so poly-THF, but if you know this, this is a good start. You'll be successful in this class, and then you can take advanced polymer synthesis classes. Any questions on this? All right. Okay, the ones that we haven't talked about and the hard ones are polyureas and polyurethanes. And they use this really funny group called an isocyanate. So if you aced organic chemistry, you probably know everything up to now, but isocyanates might be new. And the way to remember an isocyanate is I always just say the nitrogen outward, NCO. So you do have to remember NCO, and it's all double bonded, but the nitrogen is connected to the R group, NCO, and just write it out. So this is a structure that you probably have to think about, have to learn, make some flashcards. And when you react an isocyanate with the diamine, you get what's called a polyurea. And notice if you count up all the atoms, there is no small molecule byproduct in this. So this looks like a condensation polymerization, but it has one feature of an addition polymerization, which is no small molecule is spit out. And that's why I say, is this a polycondensation or polyaddition? Formally, it's an addition type reaction, but it follows polycondensation kinetics. So addition chemistry, but polycondensation kinetics, or rules of building up a polymer. So I'm not going to trap you on the exam and say, here's a polyurea or a polyurethane. Is it addition or is it polycondensation? I will ask you a direct question. You know, if I give you an isocyanate and a diamine, I'll expect you to be able to draw this structure. You want to practice that. Or if I give you an isocyanate and a diol, I'll be able, or you should be able to draw a polyurethane from that. So polyureas and polyurethanes are tricky. But the one way to remember this is that polyureas look like an amide with the nitrogen on both sides of the carbonate. Urea, you think nitrogen, okay, I get it, that's fine. Polyurethanes have that ester group and the nitrogen attached right to it in this order. The nitrogen's not over here connected to the oxygen, right? It has to look like this. And the way that I remember this stuff is that I'm able to write down what a urea, if I can get my writing here, I'm able to write down what a polyurea looks like or a urethane linkage looks like. Then I can break it apart, NCO, NCO, and all I have left is OH. And so I know a polyurethane is an isocyanate plus an alcohol, and I have NCO, and all I have left is NH2, and so I know a polyurea is an isocyanate plus a diamine. Because these polymers are so important, I'm going to expect you to be able to memorize this, but you know, this will be a couple of questions on the exam. The bulk of the information is going to be the easier ones like polyethers, polyesters, polyamides, but this is going to figure out who is going all the way in this class and learning the hard stuff as well as the stuff that I expect everyone to know. Yes.
In polyurea,
In diamine, the H's that are lost, they go to isocyanate.
That's right. So this is an addition rearrangement. So notice that this nitrogen used to have 2 hydrogens on it. And it turns out that when you react an isocyanate with an amine, here are the 2 hydrogens. You don't lose anything, but this hydrogen hops from one nitrogen to the other. That's the tricky part about this. Notice there's no small molecule byproducts in either of these reactions, which means you have to keep all the atoms in the structure somehow. That's hard. Did that answer your question? Yeah. So that's the tricky part about this slide, is that there's no small molecule byproducts, and you need to figure out where all those hydrogens go. You can't leave an atom off. Questions, comments? All right, I'm glad we're covering this today because it will take some time to settle in. All right, we're going to skip those slides, or we're not going to skip this slide. All right, get your clickers out. We are CD. It's okay to get your clickers out right when class starts, because you know I'm going to ask you a question. Yes, you have a question? On the previous slide, if I point on the right computer, it has polycondensation kinetics, the rules of polycondensation, which we'll talk about, but it's an addition chemical reaction. So it's got features of both, actually. Yeah. Okay. What class polymer is shown? This is a classic exam question. Easy chemical structure, clear answer. On the exam, this should be like 10 seconds, 30 seconds to make sure you're right. But this should not be a 10-minute question on the exam, or you should skip it if it's going to take you 10 minutes. All right. It's looking like, okay, I've got a carbonyl, I've got a nitrogen to it. I know that looks like an amide, but I have to look on the other side and figure out what this thing is connected to. If it was connected to carbon, I'd be all set with polyamide. But in fact, because I have an NH here, because of the rules of writing polymer repeat units and being able to slide those arrows, what is this structure? Polyurea. So that's tricky, but it's not a trick question because you know how to interpret this chemical structure, and you know that that is the same as this chemical structure. So I'm going to ask you on the exam about which repeat unit is equivalent as you slide those parentheses around. That's a really important principle because not everyone writes polymer structures the same. They can put the parentheses in different places. Questions? Anyone who doesn't get that question, you're lost, don't care about polymers. You can come to me in office hours if you really want to have that conversation. But this is critical that you understand this because I'm going to ask you either this exact question or a very similar one on the exam. Yes?
So then on the right side of the NH, there's another carbonyl, and then there's another NH connected to that.
Absolutely. So we can slide the monomer one way, or we can slide it the other way. And so connected to this is just what we have over here. And H, then we've got this thing, that. There's our NH again repeating. It's connected to carbonyl. And over here, we take this residue and bring it back here and write the structure backwards. NH, then we've got this thing, NH connected to carbonyl, et cetera, et cetera. Yeah. Yeah, it's not a mirror. You don't take the repeat unit and sort of flip it over. You slide it one way or the other. And we had slides on that we practiced in lecture. Other questions? Yes. How they move around. Oh. Yeah, so this is hard because the hydrogens do move around and we don't do this in any other reaction. So why don't you take a hard look at it? And we'll start with this on Friday's lecture as well. So the thing to remember when you have this funky isocyanate is that you're not going to have any small molecule byproducts. And so you need to be able to go from these two structures to this one. And we'll start with that on Friday. But take a look at it, practice it, square it up for yourselves, and then we'll continue to discuss it. All right. You're going to need all that for the exam. That is the one big topic. The second thing you're going to need for the exam is something called the Carruthers equation. And so the Carruthers equation was named for Wallace Carruthers, who worked at DuPont, and he invented nylon. And so as soon as I say nylon, you say polyamide, you say step growth, and then depending on whatever monomers you want, how do we make polyamides? What are the key functional groups? If we want to do an AA, BB polymerization, how do I make a polyamide? What's on my R1? Acid chloride. And what do I need on my R2? Amines. NH2, because we're going to do primary amines. And so what's the small molecule byproduct for this thing? HCl, right? Yep. Great. And then you can write out the chemical structure. Yes. You could use a carboxylic acid if you want. Or except if I told you it spits out water as a byproduct or it spits out HCl, then you know which monomer to use. All right. So Carruthers came up with a way to describe the molecular weight of a polymer based on the polymer reaction. And so rearranging, these should look familiar. Well, let's look at this one. You should know that the degree of polymerization is the molecular weight of the chain divided by the repeat unit molecular weight. You've got all that. We've covered that before. That works for any polymer. What Carruthers taught us is this P, and this is the definition of P. Functional groups reacted divided by functional groups initially. This is also called conversion. And this is the x-axis for this plot that you've already seen. This can be x bar n or molecular weight. What's the difference between degree of polymerization and molecular weight of the chain? How are they related? By M0, right? So this is a relationship, and so we know that molecular weight is directly related to the degree of polymerization through the repeat unit molecular weight. And so Carruthers made an equation for this. So this part of the plot that should look really familiar to you is x bar n equals 1 over 1 minus p. Memorize that. It'll actually be on the equation sheet on the exam, but you shouldn't have to look at it. But this is really important because this relationship defines the shape of that curve. By definition, it looks like this. And so this tells us, and P, what are the limits of P? Based on this plot, what can P go between? 0 and 1, right? So P goes from 0 to 1. And so when P is very close to 1, what's x bar n? That's right. Well, when P equals 1, it's infinite. When P is about 1, x bar n is a high number, right? And when P is 0, what's X bar N? 1, which means if my X bar N is 1, what do I have? A monomer, right? So we just have monomers sitting there if I have a degree of polymerization of 1. So this gives us both an equation, and since we know that P goes from 0 to 1, gives us limits as to what that equation is. And we're going to use this equation. I'm going to ask you about X bar N. I'm going to ask you about the conversion. You definitely want to take a look at this slide before class on Friday, because we're going to use this as our accounting metric to figure this out. And this is the last big idea that we need for the exam. We're going to talk about it all Friday, and then you'll have it. All right, see you on Friday. Thank you very much.